Hello students. So let's continue with our NCERT chapter 8, which is aldehyde, ketones and carboxylic acids. So today is the theory part 8 and the section which we will cover today is section 8.8. This is the disclaimer. So what is the objective of today's lecture? After attending this lecture, you'll be able to understand the topics which we are going to cover today. So today we will correlate the physical properties of carboxylic acids with their structures. Now for your reference, I have mapped the NCERT sections which we will cover today. So we will cover section 8.8, which is physical properties. Then we will solve a practice problem 1 and 2. Then we will also solve Intext question, which is 8.2 and 8.3. Moving on, solving an exemplar question, which is 8.19. And finally, we will conclude with the summary. So let's begin with section 8.8, physical properties of carboxylic acids. So first, let's talk about the physical state of carboxylic acids. So we can say that at room temperature, carboxylic acids, they can be either liquids or solids. So if I talk about lower molecular weight carboxylic acids, so they are typically liquid at room temperature. Why? Because their smaller size allows them to remain in a liquid state more easily. If I talk about high molecular weight carboxylic acids, then they are usually solids. Now why solids? Because their large size and strong intermolecular forces, they make them solidify at room temperature. Okay, so lower molecular weight, they are liquids, and higher molecular weights, they are solids. Now let's move on to the order of carboxylic acids. So lower molecular weight carboxylic acids, they have a pungent and unpleasant odor because due to their volatile nature, it allows them to easily release molecules into the air. Now as the molecular weight of carboxylic acid increases, their odor diminishes, because their heavier molecules are less volatile and they don't evaporate easily. Okay, because as their molecular weight will increase, they will become more heavier. So due to that, they are less volatile and they don't evaporate easily. So continuing with this, let's begin by discussing the polarity of carboxylic acids. Now we will talk about the polarity. So we know that the carboxyl group, which is represented as COOH, what is the nature? It is highly polar in nature. Okay, this is because of the significant differences in the electronegativity between the oxygen, carbon and hydrogen atoms. So students, this polarity, it affects the interactions of carboxylic acids with other molecules. Now if we look at this particular structure of polarity of bonds in carboxylic acid, notice the arrangement of the atoms, okay, and see that how electronegativity difference they contribute to the overall polarity. So if you see this COOH group, we can see that the oxygen is becoming partial negative. Why? Because oxygen has higher electronegativity. Okay, so it can take this shared pair of electrons. On the other hand, if you see carbon, hydrogen, you will see they have a partial positive charge. Why? Because electrons, they are pulled away from them towards the oxygen. Okay, so here oxygen has a partial negative charge, hydrogen has a partial positive charge. Similarly, carbon will have a partial positive charge and oxygen will have a partial negative charge. So this is the polarity bonds in carboxylic acids. Now the OH bond, if I talk about OH bond, then this OH bond is more polar than this carbonyl, which is COO bond. Okay. So what is the reason behind this? Why this OH bond is more polar? So if we talk about the reason, then the lone pair of electrons on the oxygen atom in the OH group, they can delocalize into the C double bond O. Okay, that is the C double bond O through the resonance. So this delocalization, this increases the electronegativity of the oxygen in this OH group, which makes it more polar. Okay, so the lone pair of electrons on the oxygen atom of this OH group, they can delocalize into C double O, a double bond through resonance, which will make the oxygen, that is this oxygen of OH group, more electronegative. Okay, is it clear? Now we will examine the melting and boiling points of carboxylic acids. So they are significantly higher compared to other similar molecular weight compounds like alkanes, alcohols, ethers, aldehydes, and ketones. Now, what is the reason why they have higher melting and boiling points? Is because there is extensive hydrogen bonding. Okay, so hydrogen bonds, they are strong intermolecular forces that require more energy to break. Okay, so you know that in hydrogen bonding there are strong intermolecular forces, and if the forces are strong, you need to provide more energy to break it. So more energy is required for phase change in carboxylic acid due to these strong hydrogen bonds. Okay. Additionally, if I talk about carboxylic acids, then they can form a stable dimeric structures. Okay, we will discuss about this dimeric structures in upcoming slide, but for now you need to know that these carboxylic acids, they form stable dimeric structures, and these dimers, they further enhance the melting point, making it higher than the expected for their molecular weight. So these dimers, they also enhance the melting point. Now if I talk about hydrogen bonding, then carboxylic acids, they form strong intermolecular hydrogen bonds, which are crucial for their physical properties. So intermolecular hydrogen bonds, okay, that is the hydrogen bonding between two molecules. Now these hydrogen bonds are so strong that they don't completely break even in the vapor phase. Okay. So if you look at this particular image over here, you will see the dimerization of carboxylic acid. So if you see over here, this is one molecule of carboxylic acid and this is another molecule of carboxylic acid. So if you see that the two molecules of carboxylic acid, they are connected by hydrogen bonds. Okay. So if you see this red line, this is the hydrogen bonding, where this oxygen has a partial negative charge, hydrogen has a partial positive charge. Similarly over here, this hydrogen will have a partial positive charge and this oxygen will have a partial negative charge. So both of these molecules of carboxylic acid, they are connected by intermolecular hydrogen bonding. So moving on to the melting and boiling points, one of the key factor that affects the melting and boiling points is the formation of dimers. So when carboxylic acid form dimers, their melting and boiling point increases. Now this is because the dimer formation, it leads to the strong intermolecular forces. So now I am talking about again and again of this dimer. Now let us understand this concept of dimerization. What is this dimerization? So dimerization typically occurs in aprotic solvents such as dimethyl sulfoxide, which is DMSO, or N-dimethyl formamide, which is DMF, or even in the vapor phase. Okay, so this occurs in aprotic solvents. Now, during dimerization, two carboxylic acid molecules, they bond through hydrogen bonds. Okay, so two carboxylic acid molecules bond through hydrogen bonds. Now, the formation of these hydrogen bonds during dimerization, this enhances the stability of carboxylic acid molecules. So this increased stability is why the dimers, they have higher melting and boiling point compared to the individual molecules. Okay, so because of this dimerization, the stability of the molecules increases, and because of this stability, they have higher melting and boiling points compared to individual molecules. Okay, so this is the concept of dimerization. Now let us discuss solubility. Okay, so we discussed melting and boiling points, we discussed about hydrogen bonding. Now let us see about solubility. So how you'll define solubility? So solubility determines how well a substance can dissolve in a solvent. Okay, if we take solvent like water. So for carboxylic acids, this property, that is the property of solubility, it varies with their molecular structure. So if we talk about lower molecular weight carboxylic acids, those with up to 4 carbon atoms, so these are soluble in water because they can form hydrogen bonds with water molecules which help them dissolve. Okay, so this hydrogen bonding, it is a strong type of dipole-dipole attraction. So because they are able to form hydrogen bonds with water, so they are soluble. So the ability to form the hydrogen bond is what make these smaller carboxylic acids soluble. Okay, so if you look at here, you will see hydrogen bonding with this carboxylic acid with water, which is H2O. Okay, so this hydrogen bond occurs when the hydrogen atom of one molecule, it is attracted to an electronegative atom like oxygen in another molecule. Okay, so if you see this H2O, this is a water molecule, and here this one molecule of carboxylic acid, and here are also other molecules of carboxylic acid. So if you look over here, this carbonyl oxygen is hydrogen bonded with this hydrogen of water molecule. Okay, similarly you will see that this oxygen of water, it is hydrogen bonded with this hydrogen of carboxylic acid. Okay, so this is because of when the hydrogen of one molecule, it is attracted to an electronegative atom like oxygen in another molecule. So this interaction is essential for the solubility in water. So now as we increase the length of the hydrocarbon chain in carboxylic acid, their solubility decreases. So as you increase the chain length, the solubility will decrease. Now why this happens? Because the non-polar hydrocarbon chain becomes longer and it makes the molecule less compatible with water, which is polar. So the longer chains, they are hydrophobic in nature. Hydrophobic means they repel water. They don't love water. So this hydrophobic nature, they start to dominate as the chain length increases. So this reduces the overall stability of carboxylic acid in water. So if you look at this image over here, you will see that how the solubility of carboxylic acid changes with the length of the hydrocarbon chain. Okay, so as I told you, the solubility decreases as the alkyl chain, non-polar alkyl chain, it gets longer. So if you see over here you have ethanoic acid. So ethanoic acid is more soluble in water because ethanoic acid has only one carbon containing methyl group. Okay, while if you look at hexanoic acid, they have 5 carbon containing pentyl group. Okay, so that is why if you see from here, this is the number of carbon chain in the this is number of carbon atoms in the alkyl chain, which is non-polar part is increasing. If you're going from ethanoic to propanoic to hexanoic, so hexanoic has the more number of carbon atoms in the alkyl chain. So that is why this hexanoic is least soluble in water, whereas ethanoic acid is more soluble in water. Okay, so as this hydrophobic nature of this alkyl chain will dominate, the solubility will decrease. Okay, so now there is one question. Compare the boiling points of butanoic acid, which is CH3CH2OOH, and butanol. Okay, so you have butanoic acid, which is a carboxylic acid, and you have a butanol, which is a alcohol. So you have to compare the boiling points. Both have the same number of carbon atoms. If you look, both have same carbon atoms. You have to explain the difference in their boiling points. Okay, so can you think of the correct answer? Let us discuss. So if we talk about the reported value, then the reported value of boiling point of butanoic acid is 163.5 degrees Celsius and butanol is 117.7 degrees Celsius. So here you can see that the boiling point of butanoic acid is more as compared to butanol. So if you see, this is butanoic acid, 1, 2, 3, 4. 4 number of carbon atoms are there. Okay, and if you look at this butanol, 1, 2, 3, 4, here also there are 4 number of carbon atoms, but the difference is in their functional groups. Butanoic acid is a carboxylic acid, whereas butanol is an alcohol. So here it is shown that a carboxylic acid, which is butanoic acid, its boiling point is more as compared to butanol. So butanoic has a higher boiling point than butanol. This is because of the formation of, first, there are 2 hydrogen bonds in butanoic acid. Okay, if I talk about butanoic acid, in butanoic acid there is 2 hydrogen bond. One is between the oxygen of carbonyl, which is C double bond O, and hydrogen of OH, of other molecule of acid. Okay, and second one is between the hydrogen of OH group and oxygen of C double bond O of other acid molecule. Okay, whereas if I talk about butanol, then in butanol there is only one hydrogen bond in butanol, that is between the hydrogen of OH and oxygen of OH for other alcohol molecule. Okay, so one is between the hydrogen of OH and oxygen of OH of other alcohol molecule. Secondly, if I talk about butanoic acid, there are dimers through double hydrogen bonding in butanoic acid. While if I talk about butanol, in butanol there is no dimer formation, which increases the boiling point of butanoic acid. In butanoic acid there is dimers. Okay, so dimers, they increase the boiling point of this butanoic acid. So this stronger intermolecular attraction due to strong hydrogen bonding, this requires more energy to break, and that results in the higher boiling point for butanoic acid. Okay, if you look at this particular diagram over here, students, here you will see there is butanoic acid. I told you in butanoic acid there are 2 hydrogen bond. So one is, if you see, this is a butanoic acid. Okay, that is C3H7, and this is the carboxyl group. So one is between the oxygen of this carboxyl group and hydrogen of another butanoic acid. Similarly, here you will see this is the hydrogen bonding between the hydrogen of this butanoic acid and the oxygen of this carboxyl group of another butanoic acid molecule. Okay, so there are 2 hydrogen bonds. Now if you look at this butanol, in butanol there is only one hydrogen bonding, that is this oxygen of this butanol and between this hydrogen of another butanol molecule. Okay, now next question is, you have to arrange the following carboxylic acid in the increasing order of solubility. Okay, so arrange the following carboxylic acid in order of increasing solubility in water. First, you have hexanoic acid, then you have acetic acid, and then you have octanoic acid. So you have to arrange in the increasing solubility order. So can you guess what is the correct solubility order? Right now only we have studied how solubility is affected. Okay, so from that can you guess that which will be the correct order? So you have hexanoic acid, acetic acid, and octanoic acid. Okay, let's discuss it. Now, if you look at this particular image, okay, so this will represent the molecular structure of the given carboxylic acid. Now, main thing which you have to pay attention over here is the length of the hydrocarbon chain in each acid. So this length of the hydrocarbon chain is what determines the solubility. Okay, so longer carbon chain will show more positive inductive effect. So as we are moving towards larger carbon chain, the polarity is decreasing, thus the solubility in water is also decreasing. If you look at this particular octanoic acid, it has more plus I effect. Okay, because it has a larger, this octanoic acid, it has a larger carbon chain. So as the chain, we are moving towards longer carbon chain, so this octanoic acid will show more positive effect or more inductive effect. Okay, so that is why the polarity will decrease. And if we are moving from octanoic acid to hexanoic acid, the length of this carbon chain is less as compared to octanoic acid. And for acetic acid, it is least. So this acetic acid will show least plus I effect. Okay, so that is, if you see this octanoic acid, this is least polar, and this acetic acid, this is more polar. Okay, so as the polarity decreases, the solubility in water decreases. So if you are moving from acetic acid to octanoic acid, the polarity is decreasing, so the solubility in water is also decreasing. Okay, so if we move forward, we will see that the solubility depends on the balance between the polar carboxyl group, which is COOH, and the non-polar hydrocarbon chain in an acid. Okay, so there should be a balance between both the groups. Further, if we see, this principle of like dissolves like is very important here. Like dissolves like means polar substances dissolve well in polar solvents. So polar solutes dissolve well in polar solvents. So as the chain length increases, the non-polar character of molecule also increases. So this means that the longer chain, they are less soluble in water because the non-polar part dominates. And as the non-polar part will dominate, it will reduce the interaction with water. So acetic acid, if you look at this acetic acid over here, this has the shortest hydrocarbon chain among the acids. So this makes it more soluble in water because the polar carboxyl group, it has a greater influence compared to the short non-polar chain. So here this polar carboxyl group, it has more influence compared to this short CH3 group. On the other hand, if I talk about octanoic acid, it has the longest hydrocarbon chain. So this makes it least soluble in water. So the extensive non-polar chain, it reduces the overall polarity of the molecule. Thus, it affects or it limits its solubility. So finally, the order of increasing solubility is octanoic acid, then it is hexanoic acid, and then it is acetic acid. So acetic acid is most soluble. Okay, so if we look at this particular order, so it reflects the balance between the polar and non-polar part of each molecule. Okay, so I hope this question is clear to you. Moving on forward, you have to write the structures of the products of following reactions. Okay, so these reactions are given to you. You have to write the structures of their products. So I'll give you some time to think, take 30 seconds, and then we will discuss. Okay, let's see the solution now. So we will start solving with first part. So first part, it is the preparation of a ketone from benzene. Okay, so we will prepare a ketone from benzene. So first let us see the net reaction. So this is the overall transformation that occurs when benzene is converted into a ketone. So look at this particular reaction. Here you have benzene, okay, and you have propionyl chloride. And the product which you get is propiophenol. So propiophenol, it is prepared from benzene by acylation reaction in the presence of an anhydrous aluminum chloride, which is AlCl3. And this AlCl3, it acts as a catalyst. Okay, so this is a net reaction which is given. Now we will see the mechanism of this particular reaction. So what is happening in step 1? In step 1, there is attack of acyl chloride on aluminium chloride, which is AlCl3. So acyl chloride, which is propionyl chloride, it will attack on AlCl3. Now this, it initiates the reaction by forming a complex that will further react with benzene. Okay, so if I talk about AlCl3, then it acts as a catalyst here, which facilitates the reaction. So if you look at this particular image, you will see the interaction between the acyl chloride and AlCl3. So this acyl chloride, it attacks this AlCl3. Okay, so propionyl chloride over here, this reacts with AlCl3 to form a complex salt over here. Okay, so you will see that this complex is formed over here. Moving on to step 2. In step 2, we will see the formation of acylium ion. Okay, so if you look at the structure of acylium ion, this is the acylium ion. So this acylium ion is formed when the carbonyl group, when this group, which is the carbonyl group, it loses a leaving group, which is AlCl4 minus. So when this carbonyl group loses this leaving group, which is AlCl4 minus, so this results in a positively charged oxygen atom. So if you'll see over here, this carbon is triple bonded to this oxygen and it has a positive charge, and AlCl4, this group has left from this complex. Okay, so this step 2 is the formation of acylium ion. Step 3 is the attack of benzene on acylium ion. Okay, so this is the attack of benzene on acylium ion. If you look over at this particular image, okay, so you will see that this benzene, it attacks on this acylium ion. So this is an example of an electrophilic aromatic substitution where an electron-rich benzene, so this is an electron-rich benzene, it attacks the electron deficient acylium ion. So this acylium ion is electron deficient, or I can say it is acting as an electrophile over here. Okay, so this electron rich benzene attacks this acylium ion. Now this attack, it results in the formation of a new carbon-carbon bond. If you see this carbon and this carbon, so this is the formation of this carbon-carbon bond. Okay, that is expanding the molecular structure. So see, after this attack, this benzene ring is now attached to this acylium ion, which is forming a new intermediate. Now step 4 is the regeneration of the aromaticity. If you look over here, then this ring has lost its aromaticity. So now there will be regeneration of this aromaticity. Okay, so if you look over here, after the initial attack, the benzene ring has temporarily loses its aromatic character, and these steps restore the aromaticity, which is energetically favorable and stabilizes the molecule. Okay, so this benzene ring now has returned to its stable and aromatic form. So this is the regeneration of aromaticity. Now the next one we will see preparation of ketone using acyl chloride. So first let's see the net reaction, the overall reaction with reactants and products. So if you look at this reaction, you have a dibenzyl cadmium which reacts with acetyl chloride and produces 1-phenyl propane 2-on. Okay, so this will produce 1-phenyl propane 2-on. So if you see, this is also called as benzyl methyl ketone. Okay, so this is the net reaction, that is the preparation of ketone from acyl chloride. So now let's talk about mnemonic. So mnemonic is a short method how from this reactant you can get the product. Okay. So if I talk about the particular mnemonic, if you see over here, then this over here, this is dibenzyl cadmium. Okay, that this is cadmium, and both side there is dibenzyl group, and here you have acetyl chloride. So if you remove this cadmium from dibenzyl cadmium and this chlorine from acetyl chloride, so if you remove this, you will get this particular compound which is 1-phenyl propane 2-on. So you are getting 2 molecules of 1-phenyl propane 2-on, and CdCl2 is you get it as a byproduct. Okay, so this is a mnemonic, or this is a shortcut method, that how from when you react dibenzyl cadmium with acetyl chloride, how you can get 1-phenyl propane 2-on. Okay, so just remove the cadmium from dibenzyl cadmium and these chlorine from acetyl chloride, and you will join this molecule and you will get 1-phenyl propane 2-on. Okay, so if we discuss about the mechanism, then here this dibenzyl cadmium, this acts as a nucleophile due to the partial negative charge on this benzyl group which is attached to the cadmium. So each benzyl group, it attacks the carbonyl carbon. This is the carbonyl carbon of acetyl chloride, and this is electron deficient because of the presence of this electronegative chlorine atom. So then this nucleophilic attack, this leads to the substitution of chlorine by this benzyl group, which results in the formation of ketone and the removal of cadmium and chloride ions. Okay, so this is how you get a ketone using acyl chloride. Now let us see the next one. Next is the preparation of ketone through hydration of alkyne. So by hydration of alkyne, you need to prepare ketone. So this preparation of ketone through hydration of alkyne, this is a name reaction, which is a famous reaction called oxymercuration demercuration reaction. Okay, so the name of this reaction is oxymercuration demercuration reaction. Now what happens in this reaction? In the hydration reaction, you add H2O. Okay, so in this H2O, the addition of H2O, it follows Markovnikov's rule. Now what does this rule says? This rule says that the hydroxyl or the OH group, it attaches to the more substituted carbon of the double bond. Okay, so if we look at the overall reaction, so in this reaction, you will see the hydration of propine. This is propine. So the hydration of propine with dilute sulfuric acid in the presence of mercuric ion. And this will finally give you a ketone, which is a acetone. Okay. Now, how this is happening? Let us look at this mechanism. That is, when you are reacting propine with Hg2+ in presence of sulfuric acid, you are getting an acetone. So first step is it includes the addition of mercuric ion to this C triple bond C bond. So first you will add this Hg2+ to C triple bond C bond. So if you look at this image, in this image you will see that the alkyne, which is the propine over here, it binds to the mercury ion, which is Hg2+, and it forms a cyclic mercurium ion. Okay, so you will see that this is the formation of cyclic mercurium ion. So this is the step 1, which is the addition of Hg2 plus to C triple bond C. Now we will see the next step. So it is the attack of H2O to cyclic mercurium ion. Okay, so this H2O will attack on this ion. So here you will see that the water molecule, this is H2O, in which oxygen has its lone pair. It interacts with this cyclic mercurium ion, okay, and the water attacks the more substituted carbon. Okay, so as I told you, it follows the Markovnikov's rule. So this water or this oxygen will attack the more substituted carbon, generating an enol intermediate. So this is the enol intermediate which is generated, and this enol intermediate is unstable. Now next step 3, we will see that is this image, there is release of one proton. Okay, that is, this is OH2 plus, which is unstable intermediate. So there is a release of proton. So you will see this is now OH. Next step, it involves the rearrangement via keto-enol tautomerism. So the enol intermediate is unstable, and to gain the stability, it undergoes keto-enol tautomerism. So here if you see, this is the depiction of the keto-enol tautomerism. So the hydrogen from this OH, it migrates to the adjacent carbon and a double bond shifts over here. Okay, so you will see that this the hydrogen from this OH, it will migrate to the adjacent carbon. Okay, and this will generate, and there is a shift of this double bond. So this is this double bond O over here. Now let's move to the step 5, which is addition of hydronium ion. So hydronium ions, they are simply water molecules with extra proton, which makes it positively charged. Okay, so here you will see, here is the addition of the hydronium ions. Okay, so now you will see the changes in the structures over here. Now moving on to step 6. Step 6, it is the release of Hg2 plus ion over here. Okay, so if you look at this particular image, so this shows the molecular structure after the release of Hg2 plus ion. So when this Hg2 plus ion is released from here, you are getting prop 1 N2 all, and this is again unstable over here. So now we again need to make this stable, and this rearrangement is by the tautomerism. Okay, so you will see that this is when you tautomerize it, that is the shifting of hydrogen from OH and the bond shifting. And finally, we get the major product over here, which is acetone. Okay, so this is the mechanism, or this is the steps through which we have followed to get final, which is the acetone. Okay, try this mechanism once by yourself. Things will be more clear to you. Now let's see the last part, which is the preparation of aldehyde using chromyl chloride, which is CrO2Cl2. So here we see the net reaction. So if you look over here, you will see this is para-toluene, okay, and the final product which you get is para-nitrobenzaldehyde. So if you look over here, this methyl group of para-toluene, it oxidizes to aldehyde, forming para-nitrobenzaldehyde using this chromyl chloride, which is CrO2Cl2. So if we look at the mechanism, then if you see over here that the chromyl chloride, it forms a complex with the methyl group. That is this methyl group of para-nitrotoluene. So this chromyl chloride, it will form a complex with this methyl group, which leads to the formation of chromate ester. Okay, this is the formation of chromate ester intermediate, which is formed at the benzylic position. So if you'll see, this is the benzylic position, and this is formed at the benzylic position. Now this intermediate is not stable, and it eliminates the hydrogen from the methyl group, and then water is added to break this gem dichloro intermediate, which is through the hydrolytic cleavage. And then this is converted into an aldehyde group, which yields para-nitrobenzaldehyde. Okay, so this is how from para-nitrotoluene you got para-nitrobenzaldehyde. Now we will see the next question. You have to arrange the following compounds in increasing order of their boiling points. So you have been given CH3CHO, which is an aldehyde group. Okay, then you have CH3CH2OH, which is an alcohol. You have CH3OCH3, and then you have CH3CH2CH3. Okay, so you have to arrange it in the increasing order of boiling points. Now, can you think or guess the right answer for this question? Okay, we will discuss it one by one. First of all, we will see the factors which are affecting the boiling point. So, first factor is the intermolecular forces. Now, these intermolecular forces, they include hydrogen bonding, dipole-dipole interactions, and van der Waals forces. So, if we talk about this intermolecular forces, then they are very crucial over here because they determine how strongly the molecules they attract each other. If I talk about hydrogen bonding, then this is a strong type of intermolecular force. Okay, and this can significantly raise a compound's boiling point. And if I talk about dipole-dipole, then these interactions are weaker as compared to hydrogen bonding. Van der Waals forces, they are the weakest. So van der Waals forces, they are the weakest. The second factor that affects the boiling point is the molecular size and shape. So large molecules means they have larger surface area. So more surface area can have higher boiling points because of the increased van der Waals forces. So the shape of the molecules, they can also influence that how closely molecules can pack together, which affects the boiling point. Now let us one by one see all the molecules. First, if I talk about propane, which is a simple alkane. So propane is a non-polar molecule, which means that it doesn't have a significant difference in the electronegativity between its atoms. So that is why the lack of this polarity affects its intermolecular forces. Now propane, as we have discussed, it is a non-polar, so it only exhibits weak van der Waals forces. So van der Waals forces, they are the weakest type of intermolecular forces, which means that propane, they have relatively lower boiling point compared to the polar molecules. Okay, so this propane will have the lowest boiling point. Now, because of this weak van der Waals forces, this propane will have the lowest boiling point. This is because the energy which is required to overcome these weak forces, they can convert propane from a liquid to a gas. Okay, so less energy is required over here to convert propane from liquid to gas. Now we will see this ether molecule, which is dimethyl ether. Now, unlike propane, this dimethyl ether is a polar molecule. So this polarity, it introduces different types of intermolecular forces compared to the non-polar molecules. So if I talk about dimethyl ether polarity, means it has a weak dipole-dipole interactions. So this dimethyl ether, they have weak dipole-dipole interactions. These interactions, they are stronger than the van der Waals forces. But on the other hand, they are weaker than the hydrogen bonds. So this is due to the presence of dipole-dipole interactions without the additional strength of hydrogen bonds. Okay, so see over here, there is no hydrogen bonded. There is no hydrogen bonding. Okay, for hydrogen bonding to occur, there must be a OH or NH bond. But if you look at this dimethyl ether, there is no OH or NH bond. So this absence of hydrogen bonding limits its boiling point compared to the compounds that can form such bonds. So this gives dimethyl ether a higher boiling point than propane. So that means propane will have, it gives higher boiling point than propane. That means this dimethyl ether will have higher boiling point than propane. Now let's see other molecules. Then we have acetaldehyde, which is a aldehyde. So it is a polar molecules because of the presence of highly polar carbonyl group. Now this has a highly polar carbonyl group which creates an uneven distribution of electrons within the molecules. So acetaldehyde, they have a strong dipole-dipole interactions among it compared to other molecules because it has a more polar carbonyl group and lacks hydrogen bonding. Okay, it has a polar carbonyl group but it lacks hydrogen bonding. So no hydrogen bonding is present. It means that it cannot form the very strong intermolecular hydrogen bonds, making dipole-dipole forces the dominant intermolecular force. Okay, since there is no hydrogen bonding present, so we can say that dipole-dipole forces is the dominant intermolecular force. So acetaldehyde dipole-dipole interactions are considered significant enough to give it a considerable higher boiling point than the non-polar or less polar molecules like dimethyl ether. Now we will see another molecule which is an alcohol, which is an ethanol. So we know that ethanol is a polar molecule. Now this ethanol forms an extensive hydrogen bond because of the presence of this OH group, okay, which has a much stronger force than dipole-dipole interactions. So this hydrogen bond results in the association of the molecules. Now because of the strong hydrogen interaction among the molecules, ethanol has the highest boiling points among the given compounds. So ethanol will be placed first. So finally, if we conclude, then boiling point increases as the strength of intermolecular force increases. This is because stronger forces require more energy to break, which leads to higher boiling point. And if we look at the order of increasing boiling point, we can see that ethanol, it has the highest it has the strongest hydrogen bonds which give it highest boiling point. Okay, whereas propane, it is weakest. Propane, it has the weakest boiling point because in propane there is weak van der Waals forces. Okay, so we discussed one by one each molecule and we saw the factors that affect their boiling points. Now let us see one more question, which is an exemplar question. Why is there a large difference in the boiling point of butanol and butane 1-ol? So you have to compare between an aldehyde and an alcohol, which is butanol and butane 1-ol. So if you look at the solution, let's start with butanol, which is an aldehyde. So we know that aldehyde has a polar carbonyl group. So this polarity affects how molecules interact with each other. So the carbonyl group in this butanol is polar, means it has a partial positive and a negative charge. So this polarity allows for dipole-dipole interactions. Okay, and these are important in determining the boiling points. So in butanol, the intermolecular forces, they are primarily dipole-dipole interactions and London dispersion forces. So these dipole-dipole interaction, they occur between polar molecules. While if I talk about London dispersion forces, then they are present in all the molecules regardless of the polarity. These forces in butanol, they are moderate in strength, which means that they don't require a lot of energy to overcome. So that is why we can say that this butanol, it has relatively lower boiling point compared to butane 1-ol. Now if I talk about butane 1-ol, which is an alcohol, so alcohol has an hydroxyl group. So this hydrogen bonds, the hydroxyl group of OH in butane 1-ol is responsible for the hydrogen bonding. So hydrogen bonds, they are a type of dipole-dipole interactions, but they are much stronger because of the presence of hydrogen atoms which is bonded to electronegative atom like oxygen. So in butane 1-ol, the intermolecular forces include hydrogen bonding and London dispersion forces. So hydrogen bonds, they are particularly strong, which makes them dominant force in determining the boiling point. Okay, so similarly, it is written over here that the hydrogen bonds, they are much stronger than the regular dipole-dipole forces. So that is why butane 1-ol has a higher boiling point than butanol. So this strength means more energy is needed to break these bonds during boiling. Okay, so if you look at this particular image, you will see that this is intermolecular hydrogen bonding in butane 1-ol. Okay, so this is the intermolecular hydrogen bonding in butane 1-ol between the hydrogen of the OH group of one alcohol and with the oxygen of OH group between another alcohol. Okay, so this is the hydrogen between this alcohol and between this oxygen of another alcohol. So as a result, we can say that hydrogen bonding leads to much stronger intermolecular attractions. Okay, and this is crucial because hydrogen bonds, they are a type of dipole-dipole interactions that occur when a hydrogen is bonded to a highly negative or highly electronegative atom like oxygen. So this stronger interactions require more energy to break, and this means that converting the liquid into gas, it takes more energy, which directly affects the boiling point. So therefore, we can finally conclude that butane 1-ol has significantly higher boiling point than butanol. Now we will summarize whatever we have studied. So we talked about the physical state of carboxylic acids, where we saw that lower molecular weights, they are typically liquid at room temperature. This is because fewer carbon atoms, which make them less dense and more fluid. In contrast, I told you that higher molecular weight acids, they are solids because increased number of carbon atom leads to stronger intermolecular forces, which makes them more rigid. Then these acids, they also have a pungent odors which tend to decrease as the molecular weight increases. And this is due to the volatility of the compounds. That is, lighter acids evaporate more easily, releasing their odor. Then next we discuss about polarity. So the carboxyl group, which is COOH, is highly polar. Okay, so this group is highly polar because of the electronegativity difference between the oxygen and the hydrogen atoms. Then we talked about the melting and boiling points. So carboxylic acids, they have higher melting and boiling point compared to other compounds of similar molecular weight. Okay, and why this is? This is because of the extensive hydrogen bonding that occurs between molecules. So these bonds require more energy to break, which leads to higher melting and boiling point. Okay, and then we also talk about the ability of carboxylic acids to form stable dimeric structures through hydrogen bondings. Then we talked about solubility. So the lower molecular weight acids up to 4 carbon, they are water soluble because the polar carboxyl group, they can form hydrogen bonds with water. Whereas as the carbon chain length increases, the solubility decreases. So the longer carbon chains, they are more hydrophobic, means they repel water, which reduces the solubility. So thank you students for attending today's lecture. I hope the concepts which we have discussed are clear. Hope you all have a good day. Thank you.